Kymeta is a very blessed and unusual company, and our mission is to bring a revolutionizing and transforming set of new technologies into widespread and common adoption in the satellite communications industry. So, who we are is a company that's been leveraging the field of metamaterials. Metamaterials grew up about 10-15 years ago when we all thought we were going to have optical computers and optical switches for our networks. A lot of money was invested in transformative optics, trying to make light do things that it didn't do in nature. Make 90-degree turns, U-turns, bend around things. You may all be familiar with the invisibility cloak. I'm proud to say that our CTO and founder built the invisibility cloak at Duke University as part of his graduate work. When Dr. Kuntz finished at Duke as one of the new freshly minted experts in the field of metamaterials, he looked at his advisor, Dr. David Smith, and says, well, you created me. What am I supposed to do? I guess I can go be a college professor and teach metamaterials to other folks, but where and how can you aim me? And he sent him out to Intellectual Ventures in Redmond, Washington. Intellectual Ventures is a company founded by Dr. Nathan Myhrvold, the former CTO of Microsoft, who had been innovating in the field of intellectual property. He's been painted with all kinds of brushes for his efforts to try and find ways to commercialize the field of intellectual property. But one of the key aspirations he had was when he found a unique technology that might have a special and truly groundbreaking application in whatever field of endeavor, then they would try to organize it and spin it off from their core. Kymeta is the second one of those companies, and what Dr. Kuntz found when he went to IB and spent about 1.5 years in the lab was that metamaterials and the physics kit that was created to manipulate light at the, whatever station of the very broad electromagnetic spectrum, would that physics toolkit still apply as we came lower and lower in frequency down into the radio frequency domain? And the very good news for all of us is the answer was yes. So what has happened on the back of that was the creation of a new generation of metamaterial-based antennas. And that is allowing Kymeta to pursue some very significant new contributions. We do hope for the best and for the positive benefit of the entire satellite industry will allow us to, for the first time, take a step forward kind of out of the shadows that the satellite industry has fallen under with the cellular industry, the terrestrial wireless industry, fiber optic industry, and be able to assert ourselves back into a much more predominant and active place in the daily lives of pretty much everybody on the planet. And how we're doing that is through the creation, as we'll talk about in a few minutes, of a type and kind of antenna technology that's completely software defined, has no moving parts, and is flexible and adaptable to just about any environment you may want to put it in, whether that is on a ground-based terminal or on a satellite. And what this is going to do is literally transform many of the constraints and challenges that we've had to wrestle with, both in LEO applications, MEO applications, GEO and HEO applications. So whether we're trying to take a fixed satellite service and move it into a mobile environment, or take a moving satellite and apply it to ground stations that don't care whether they're fixed or moving, but can maintain a continuous link. So many of the failures of our industry over the last decade and a half, teledesic being the most notable, if we would have existed then, perhaps life would be different. So as we came together and spun out of Intellectual Ventures, we were blessed to be able to attract some extraordinary sponsorship. Bill Gates is our leading shareholder as an individual. This is an investment from Bill Gates, Inc. And Bill also sits on our board of directors, something he does not do very often. And I think it makes a very strong statement about his interest and belief in what the future of this industry and the transformative power that Kymeta is bringing forward. Lux Capital, an extraordinarily talented group of young entrepreneurs and investors in New York City. No social networking applications for them. These guys are hard science all the way. I encourage you to go look at their website. extraordinary young investment firm. And also we've been blessed with Liberty Global. Liberty Global came our way due to their investment in O3B, and they looked at what the possibility was of Kymeta's ability to have a beam-forming satellite, eliminating the need for them to have mechanically steered pairs of antennas to maintain connection with their satellite to deliver the services that they're looking to do. So we've just passed about 120 employees. We're based in Redmond, Washington, and if you have the opportunity to come out and visit with us, we'd love to coordinate a visit and let you take a look at some really interesting and transformative new technology. So recently, last Sunday, I had the privilege of being invited, thanks to Susan and Charlie Schott, somewhere here in the room, to attend a symposium on the history of one Arthur C. Clarke. And it gave me pause, and I put this slide in here as I was thinking about some of our hubris inside Kymeta. Dr. Kuntz early on kind of launched a question or a statement: why do we have geosynchronous satellites? It's because we don't have very smart antennas. And as I thought back on the incredible contributions that Dr. Clarke made to all of us, I thought, well, let's take a step farther back. And that incredible device, the gold standard of antennas, the parabolic, when you start thinking about just how extraordinary that piece of technology is and how far back it goes, I had the privilege a few years ago to go to the Marconi Museum in Milan as part of the Technology Museum. And I was stunned when I walked in and I looked at the very first spark transmitter. And what did I see behind these two carbon rods? A piece of bent copper parabolic reflector. So the first radio used a parabolic reflector. So in 114 years, if you look at the current DTH subscriber dishes that proliferate around the world, we haven't made a lot of progress until now. And some of the challenges that have been associated with the use of parabolic antennas as we try to move into the mobile world is obviously enough. They're large, they're heavy, they're costly to integrate into gimbal antennas, and it makes it really quite difficult to deploy them efficiently and cost effectively for a lot of the missions that companies like ours want to address. So that leads us to where we are now. So this is the first product that Kymeta has worked on. This is a portable satellite terminal. It's about the size of a large laptop, and it's basically a BGAN style device, the L-band portable terminals that Inmarsat has sold around the world, but it has VSAT speeds, and it operates at Ka band. So that will be kind of a cornerstone of where we go addressing this technology into literally all kinds of fixed, portable, and transportable solutions. So we're often asked, we'd really like to see this metamaterial. Well, unfortunately, there is no such thing. Metamaterial is not a thing. Metamaterial is a field of endeavor. It's much like saying nanotechnology. But our implementation of the toolkit that metamaterials represents has allowed us to generate and make beam-forming, software-defined, electronic, holographic beam antennas. And if you look at the cartoon there on the left, what you'll see is a traveling wave coming through a standard waveguide, and then irises that open up with a tunable dielectric, illuminating different patterns of sub-wavelength resonators on the surface of our antenna. And by tuning on and tuning off different patterns of what we can call pixels, because our technology is very similar to digital display technology like this laptop computer screen I'm looking at. And our pixels are big. Our pixels are quarter wavelength resonators. But we take these sub-wavelength resonators and combine them into different patterns on the surface of this antenna dynamically, syncing with the phase and creating a beam which, depending on what patterns of those pixels we tune on or tune off, can steer the beam in azimuth and elevation. That is extraordinary. And when I first was introduced to this company, in my initial interview to become the CEO, I'm normally a guy who starts his own companies. I don't have to interview. I've seldom interviewed in my life. I'm not a good interviewer. And I had a real problem because I realized about 5 minutes after meeting Dr. Kuntz that I want this. And fortunately enough for me, after several months of the recruitment process, they decided that that was a good idea. And I've been honored and privileged to have been handed the responsibility to take this company forward. On the right side, you'll see basically three primary modes of operation that we find application for in the early productization of the technology. So the continuous tracking mode, which obviously is on any mobile platform that needs to keep a steady link to a fixed satellite. Instantaneous switching mode. You've all seen on DTH antennas how they have multiple LNBs now to look at multiple satellites. Well, with our technology, that same antenna just can switch electronically between whatever channels you might want to look at. And if you happen to need to see two of them at once, we allow two beams. So we have some very, very interesting new capabilities that have just not been possible before. And obviously enough, the continuous tracking mode is one of our real claims to fame, which we'll be demonstrating here locally with O3B this coming September, which is an actual single antenna tracking off the multiple satellites that O3B has moving across the sky in their medium Earth orbits. I'm pretty sure it might find its way into the Smithsonian Institute one day. This is the first transmit and receive metamaterial demonstration that we did last December 10th. It was very, very fun for us after many, many months of working in the lab and working in the anechoic chamber to have the technology finally to a place where we could take it out and point it at a live satellite in the sky. We applied to both the FCC and CRTC in Canada to get permission to light this thing up. The Canadians beat the FCC to the trigger by about 2 weeks. So we went up to Canada at the Telesat Canada's teleport in Vancouver and did our initial communications test. What was really fun for me as the guy who would be answering all the questions is it was a rainy, sleety, snowy, horrible weather, thousands of foot thick cloud deck day. So nobody could come back and say, oh yeah, that was probably clear sky. It was not. So as we move into what does this mean in terms of market opportunities, obviously enough, we think that the long pole in the tent for our business opportunities and for the industry at large is taking what used to be fixed satellite services and making them applicable to very broadband mobile communications. So whether that becomes over-the-horizon drones for military or commercial applications, whether that's maritime applications, we've had some very interesting experience in the yachting industry. We worked with a small systems integrator last September at the Monaco Yacht Show. We wanted to go do some research to see if there was a market for us there. And so we had some mock-ups done. We had some graphics showing a before and after of a mega yacht with the traditional mushroom farm up on top of this incredibly sleek vessel. And then what ours looked like, which were conformal and flat and pretty much invisible. And we had a lot of unintended consequences come and visit us, which was all of our friends in the industry that sell those gimbaled antennas were surrounding us. Many of them are our friends, many of them are our pending customers, and not one of them made sale. Because everybody who came said, I want that. We were ready to sell anything. So it was, including, by the way, the guy who owned the vessel, which we had done the mock-ups on. Unbeknownst to us, that was owned by the Emirates out of Abu Dhabi. Anyway, you've seen obviously on the top of your commercial airliner recently the gimbaled apertures that we put on aircraft to make connectivity to satellites. These are typically swept antennas. They have an aperture about yay big, and they're steered mechanically, pointed at the satellite. You've noticed probably the standard line signal loss due to normal aircraft movement. If you get near the equator around the world with one of those aircraft, that sign shows up all the time because there's a thing called the keyhole effect, which makes it very, very difficult for these antennas, which are very nicely, tightly defined east and west, but because the size of the aperture is so small, the lobe of the antenna is very soft, north-south. And as you get closer and closer to the equator, you can be very tightly aimed on the orbital arc, but in the other direction. You're now illuminating multiple satellites, which creates a tremendous interference issue. We don't suffer that. And the reason primarily is because we didn't have to build a small antenna to fit under a big radome. Our antennas are conformal to the skin of the aircraft. And we get the whole surface area that huge radome fits to add aperture. So the Kymeta alternative to the traditional gimbaled swept arrays is we get a massive size antenna, allowing a much stronger link margin and much higher data rates than the traditional gimbal antennas. Moving over into the connected car world, we've been discovered by the auto industry. There have been a number of failed or marginally successful attempts, and some very successful attempts, things like Sirius XM. But around the world, there have been initiatives to put video into the automobile. So the idea of infotainment via satellite into the car was where all the interest was. And we started down that road thinking that was what everybody wanted. But we were disabused of that perception very, very rapidly by the auto industry, who began to share with us their pain. And their pain is the average automobile today lives for 15 years. The second part of the pain is the average automobile today has over 100 microprocessors on board. And the only way to update, do software fixes, firmware upgrades, is at the dealer with a plug-in. So it's the SOTA and FOTA, the software over the air and the firmware over the air, that have become the driver of what is now a very strong relationship that we've created with the global auto industry, and helping, I think, in the future, the satellite industry to have a whole new market application. 77 million vehicles a year created annually and turning over. Now think about the computing environment you had 15 years ago, if you had to keep it working today. So Microsoft just shut down XT support, I believe, a few months ago, and a lot of people are complaining about that. Well, if you had a car, and that car had to be maintained and updated, the idea that that could be continuously done very, very cost effectively, is nothing is more cost effective than satellite communications for one-to-many distribution. Moving to transportable and portable, that first suite of products that Kymeta is bringing forward, competing against the suitcase transportables and the erectable antennas. We think that many of the environments that these systems are being aimed at really need fast setup, they really need instant on, and they don't have time to go through a cumbersome process of setting these things up to get communications established for whatever might be happening, be it an emergency or a fire that an electronic news gathering crew needs to talk about. Nonetheless, our system is literally instant on. We turn it on, generally aim it in the direction of the satellite, goes through a quick software-driven seek. The antenna knows where it is on the planet, it knows its orientation, it knows where the satellite is supposed to talk to is, and our ability to lock onto that satellite is very, very rapid. Taking that capability into the DTH world and the VSAT world. The VSAT industry tries to sell oftentimes into places they really don't want to send the tech. A lot of the times they need connectivity in a place that puts professionals in harm's way. So the ability to have a self-installing, self-initializing VSAT has become very interesting to several of the operators around the world that we've been privileged to talk to. On the DTH side, we didn't think we had any game there. We thought we would be too expensive and not very likely to penetrate a world where your current generation of technology is a stamped metal dish and an LNB that probably costs $15 wholesale. DirecTV disabused us of that perception. The cost of the truck roll and the second truck roll and the customer churn is so extraordinary that the ability to have a user self-installed antenna, and an antenna that isn't going to need a truck roll when the hurricane comes through or the heavy thunderstorm comes through and knocks it ajar and starts to make their perception be marginal, turned out to be an extraordinary total cost of ownership advantage that we enjoy. Moving into the next major market sector we look at, non-geosynchronous satellites. The O3B system we talked about earlier. One of O3B's primary market segments is cellular backhaul, because with the lower altitude satellites, the latency is lower and they're able to offer a higher quality of service for the voice-centric services. But historically, they required a very large and cumbersome installation to track the two satellites and make that return path. And then kind of the future piece of this is on satellites themselves. If you think about the movement towards small satellites, single sensor payloads for Earth observation, small satellites with any form of a high gain antenna are typically going to have a mechanically steered antenna or a very high power consumption phased array. And anything that's mechanically steered on the satellite is going to create orbital perturbations, it's going to be a pain to deal with, and it's going to shorten the life of the satellite. With a no moving part software-defined antenna, we think inter-satellite links and backhaul for high bandwidth sensors that currently are suffering with finding ability to get enough bandwidth to downlink the kind of resolution that's required in real time is a real breakthrough. And we've got several conversations going in industry today to bring our technology into orbit. And then the lines of business and the products, just to reiterate, transportables, we think we have a very significant opportunity with first responders, with electronic news gathering organizations, field service engineers for comms on the pause, and transportables and portables. Our mobiles will start in the maritime space and the aeronautical space, ultimately moving into the connected vehicle. Fixed and DTH, we believe, are markets that will require us to move into our mass manufacturing capabilities. And I think it's important to share with you that the technologies we're implementing are completely amenable to being manufactured over existing mass communications or mass electronics, consumer electronics manufacturing techniques. So liquid crystal displays, such as we all have on our laptops or in our living rooms, are our manufacturing technology of choice for our next generation. So we've entered into a research and development relationship with Sharp in their labs out in Kymeta, Washington. And the first articles have come back from that a few months ago, very promising. We went to Japan. Dr. Kuntz shared a story of going over to meet the head management at Sharp in Japan, thinking he was going over there to sell our opportunity to them. And he called me from Japan. He said, I thought I was here to convince these guys of why they should work with us. I didn't know it was a victory lap. And it was already done. The management at their U.S. R&D center has says, you guys have to pay attention to this. And so we've entered into a strategic relationship that will be able to see these antennas manufactured on existing assembly lines that can build millions and millions of them. So that will be our phase 2 of the growth of this company as we go from the hundreds to the thousands to the tens of thousands, and then immediately jump up to the ability to address markets that require and demand of us millions of volumes. At the end there is the OEM modules. Kymeta has a lot of people saying a lot of things about us, mostly kind, but sometimes not so much. And there's fear when change shows up, and people have kids to raise and mortgages to pay. And I've spent a good portion of my time on podiums around the world letting the industry know that our doors are open to all comers. And we have as our primary aspiration the ability to sell our technology and license our technology to all comers on appropriate terms, to literally be a positive contribution to helping, literally be a rising tide to help lift all the boats. And the timeline for that, for us, the commercial availability, we'll have our first products, probably formal announcements and product rollouts look like they'll take place at Satellite 2015 here in town. We'll be doing trials and demonstrations between now and then with a number of our commercial partners. And long term, I think the big move into mass market capabilities is sort of Q3, Q4 2017. And our promise to this industry is that we're here to try and improve the efficiency of satellite communications writ large across all segments and sectors of the industry. We think we can improve the economics of our industry, reduce the truck rolls, increase the penetration, and literally expand and open up new markets that have been pruned off to us. We've been operating well behind the cellular industry. I don't know, does anyone in this room have the statistic I've been suffering to find, which is how many VSATs are there in the world today? And closest I get is about 30 million. If anybody knows, I'd love to know, to have a real guess. How many cell phones are in the world today? 3.5 billion. And I think there will now be a chance for the satellite industry to move from tens of millions to hundreds of millions and potentially billions of devices in the public's hands around the world over the coming decade. The announcement from the likes of Google and some of the initiatives from Facebook, new entrants in our industry, obviously exciting. We hope that they succeed. We hope that they also make their contributions to expand our industry. But it is a time for a new wave that is coming very fast. It's a very big wave. We think we can be a significant catalyst to helping that wave be successful. And we're here to keep our doors open to any and everyone who wants to participate with us to those ends. So with that, I thank you so much, and be happy to answer any questions you may have.
I'm curious to does the materials that you're able to use, do they have flexibilities, or are there surface tolerance issues that would either preclude or allow unfurling?
The good news is it's a software-defined aperture. And are you familiar with willow glass, Corning's willow glass? Like they use, this is bendable glass. We're working to that end to use flexible substrates to build these DFT components on. So at least in 2 dimensions, if not 3, we'll have flexibility. We know for sure. And because it's software defined, we've already had one of our brilliant young scientists do the math to say if it's not flat and the antenna needs to create a beam like this, what happens if it's curved? Can you still congeal the beam? The answer was yes. Please.
Bert, I know some automakers, particularly the ones that have lots of microprocessors in their car, are concerned about the security of the microprocessors. What impact will come out of this product after that? In terms of, is it going to have enhanced? Is that also a concern of coming out of, or? Security
is, in all communications companies, top level always. I think the auto industry today is suffering with the cost. Toyota's put numbers in front of us like $8.5 billion of burden overhead to keep up with that stuff every year. I think the ability to do an over-the-air upload will certainly only happen if we can demonstrate that it's fully secure at both ends of that link. You know, and I mean, the hackers are coming. They're already here. I don't know. They probably just haven't found a reason to hack our cars yet. But when they figure out how they can pay themselves by hacking our cars, they'll be hacked. Any other questions? Sure.
Yeah, you mentioned these are all Ka band.
No, Ka is where we began.
Okay.
So the technology is agnostic to spectrum. We could build a 600 megahertz version of this. It would be about the size of 3 of these tables put together. It's frequency dependent. So we believe the utility value of our current generation of implementation is from X band and above, so 10 gig and up. There are probably more efficient and cost-effective ways to do antennas below 10 gig currently. But we think we have a very distinct advantage. Ironically, the higher in frequency we go, the more efficient the technology becomes. So we're looking at things, like terrestrial cellular backhaul and near-field communications and Gen 5 cellular up in the millimetric microwave bands for short-range communications, with postage stamp size antennas.
I am more interested on the satellite-mounted antennas, and I see that from your timeline, you are looking at launching it on in 2018 or 2017.
That one is all going to be, that's ours. If we're responding to interest and information requests from outside, that could change depending on interest we find.
Yeah, and being on this geosynchronous satellite, for example, the power is always a major concern for us. Is there any limitation on your antenna in terms of what power it can handle, high power and all that, when you go to Ka band and other places?
The antennas themselves, the creation of the holographic beam is very low power. We use USB ports off laptops to drive the test articles today to make the antenna load. The power that goes into that is independent of the load creation. And the highest we've tested so far is 20 watts. But theoretically, in calculations we've done, looks like it'll easily absorb over 200 watts.
I I see. So there is any limitation? I mean, what maximum power it can handle?
I think the power constraints would probably have to do with coupling at the resonator level, and so we just haven't done that research yet. But we're pretty comfortable. Anything in the traditional consumer electronics realm will be fine.
Maybe time for one more question.
Just as a follow-up, I noted one of the slides said that the antennas were naturally space hardened, and I wondered if you could explain what was meant by that.
So we use as our tunable dielectric to tune on and off the resonators. We use liquid crystal, and liquid crystal in its native form is naturally immune.
Thank you.
Thank you so much. Appreciate it.